A system of equations is a set of equations with different variables being solved simultaneously. For example, within this system of equations, there are two equations, which are x plus y equals 2 and x minus y equals 3. This system has two variables and two equations, but as long as there are more equations than there are variables, we can solve it. However, if there are more variables than equations, some variables will have an infinite number of possible values. This will be elaborated later on in the video. Such systems can be solved graphically or algebraically using the method of substitution and elimination. Substitution may be preferable when equations are being transformed and rearranged. It is also often used when elimination is too time-consuming. On the other hand, elimination could be used if substitution involves a lot of fractions or tedious calculations. If this is your first time learning about this concept and these methods of solving equations may feel unfamiliar and exotic at first, but just remember that practice makes perfect. Firstly, we could solve by graphing. There are generally two steps to this method. Firstly, we have to graph the functions. This can be done by typing your equation into an online calculator such as Desmos, or you can use a physical graphing calculator. Second of all, we have to find the intersections, which are the solutions to the system. There can be three outcomes. The first one is that there is no solution, which means that the two lines do not intersect. For example, parallel lines. The second outcome is one or two solutions, which equals intersecting lines. The third outcome is infinite solutions, or undefined, which is just the same line over the same line. These three outcomes are only existent within linear lines or quadratics. Any functions of a further degree, such as a cubic function, will be different. In a system with two linear or straight lines, there can be 0 or 1 solution. We can say that a graph has 0 solutions if none of the lines intersect. For instance, two parallel lines would never intersect, thus there exists no solutions. It is important to note that within a system with no solutions, there are two parallel lines, which means that the two lines will have the same slope. However, if there are two straight lines that do not have the same slope, they must intersect at some point, and only once. Therefore, there is only one solution. A linear line and a quadratic can form three total outcomes: 0, 1, or 2 solutions. As you can see on the images, 0 solutions means the line does not intersect the curve. 1 solution means the line just barely touches the point on the parabola, which is the curve. And 2 solutions, the most commonly seen, occurs when the line intersects 2 points on a parabola. Now that we've covered the basics, we can try a hand at a sample problem. Solve the system with y equals negative 2x squared minus 16x minus 26 and x squared plus 8x plus 19 equals y. To keep it simple, we'll name the first equation equation 1 and the second equation equation 2. Firstly, we have to convert these quadratics to vertex form so we can graph it more easily. Watch our video on quadratics if you haven't already to learn how to make this conversion. Thus, after the conversion, we obtain the following equations, with the first equation being a red line and the second equation being a blue line. When plotted on a graph, you can clearly see that these two parabolas intersect at points -5, 4 and -3, 4. It is important to be cognizant of the fact that graphs are oftentimes slightly misdrawn or misinterpreted, indicating that without a graphing calculator, solving systems via graphing tends to be quite an arduous process, especially if there are decimals involved. Therefore, we would usually use the method of substitution or elimination. Substitution is much more practical and intuitive than solving graphically due to both its concise process and practicality. There are two main steps to this process. First, we rearrange one of the equations to isolate one variable. Second, we substitute the variable into the second equation and calculate to obtain the solutions. For example, we have the system of equations in which the first equation is x times brackets y plus 1 close brackets equals x cubed minus x squared, and the second equation is x squared plus 8x plus 19 equals y. First, we will isolate y in the first equation. To achieve this, we would divide both sides by x to come up with the equation of y plus 1 equals x squared minus x. Then, we minus 1 from both sides to finally come up with the equation of y equals x squared minus x minus 1. Next, we would substitute y into the second equation. If we do this, we will come up with the equation of x squared plus 8x plus 19 equals y, which equals x squared minus x minus 1. In this case, y is substituted by x squared minus x minus 1, so make sure that you don't write the y into the equation. If we simplify this, we would come up with 8x plus 19 equals negative x minus 1. Then, if we minus both sides by 19 and add x to both sides, we would come up with 9x equals negative 20. Finally, if we divide 9x by 9 and negative 20 by 9, we would come up with the final answer of x equals negative 20 divided by 9, which equals to approximately negative 2.22. We can also verify this answer graphically as shown in the bottom right hand corner. It is important to notice that the y value or y coordinate of the intersection of the two graphs may be calculated by plugging in negative 2.22 for x in either equation. Finally, we have the method of elimination, which works because coefficients of the same variables can be combined. There are three main steps to this method. Firstly, we have to rearrange the equations to align the variables top and bottom. Secondly, we add or subtract the coefficients of these variables in such a way that it can entirely eliminate one of the variables. Thirdly, we continue solving for the variable that is left over. For example, if we have the system of equations of the first equation being 3x plus y equals negative 9, and the second equation being 4x squared minus x plus y equals negative 9. In elimination, the coefficients of matching variables are added or subtracted to eliminate variables and leave only one variable for us to solve. In this case, we subtract the two equations because that cancels out y. Coincidentally, it also cancels out the constant negative 9. Since x squared does not exist in the first equation, the coefficient of x squared would be 0, and we get 0x squared minus 4x squared equals negative 4x squared. Likewise, 3x minus negative x equals 4x, and y minus y equals 0, and on the right hand side of the equal sign, negative 9 minus negative 9 equals 0 as well. From the highlighted answers above, we obtain the following equation: negative 4x squared plus 4x plus 0 equals 0. We rearrange and simplify it into negative 4 times brackets x squared minus x close brackets equals 0. Now, we solve for x. We can factor out the x in x squared minus x equals 0 to make x times brackets x minus 1 close brackets equals 0, and therefore x would equal 0 and 1. Plugging 0 and 1 back into either equation, we find that y equals negative 9 and negative 12 respectively. Thus, the solutions to our system are 0, negative 9, and 1, negative 12. This answer can be verified graphically as well. In the quadratic formula where ax squared plus bx plus c equals 0, the discriminant, which is b squared minus 4ac, may be used to determine the number of possible solutions in the system, which is 0 solutions, 1 solution, or 2 solutions. Here are the rules of the discriminant. If the discriminant is equal to 0, then there may only be one solution because the root of 0 equals 0, and thus the plus or minus makes no difference. If 0 is less than the discriminant, there are two solutions, as the plus or minus would give two values. If the discriminant is smaller than 0, there are 0 real solutions because the root of a negative number does not exist in the parameters of real numbers. We can use the discriminant to guess whether the equations actually have solutions before we solve them, saving us valuable time. For example, we may be asked to determine the number of solutions for y equals x squared plus 8x plus 19. Using the discriminant, we get b squared minus 4ac equals 8 squared minus 4 times 1 times 19, which is equal to negative 12. Since the discriminant is negative, we know that this quadratic equation has no solutions and does not touch the x-axis. Similar to two-variable systems, three-variable systems can be solved with the same methods: graphing, substituting, and eliminating. However, instead of being represented in a two-dimensional plane, we use a three-dimensional graph. This means that instead of only having lines, it can have a line or a plane, which is a flat surface that extends to infinity in all directions. Every line equation on a 2D graph represents a plane in the 3D graph. This is because only two variables exist. This 3D graph represents the y equals x plane. A plane intersecting another plane will result in infinite solutions, while a plane intersecting a line will result in 0, 1, or 2 solutions. However, if three planes exist on a graph, there can be 0 solutions, all parallel, one solution, which all intersects at one point on the x, y, or z axis, or infinite solutions, which means planes intersect at a line or they are all the same plane or line. Let's try a simple sample problem of a three-variable system. The three equations of the system are 2x plus y plus z equals 7, 2x minus y plus 2z equals 6, and x minus 2y plus z equals 0. Though all the equations look daunting and confusing, we can break it down into a few simple steps. First, we use elimination by subtraction to eliminate the x in the first and second equations. Second, we multiply both sides of the third equation by 2 to obtain 2x minus 4y plus 2z equals 0, so we can subtract x. Third, use elimination again to eliminate x in the second and third equations. We then multiply the equation obtained in step 1 by 2, so we can use elimination by addition to cancel out y. 5. We isolate and solve for z. We plug in z for the equation in step 1 or step 3 and solve for y. We can do this because x has already been eliminated, so we only have y and z in our equation. We have calculated the value for z, and now we just calculate the value for y. Plug in y and z for any of the three original equations to solve for x. Finally, we obtain our answer x, y, z, which is equal to, respectively, 1, 2, and 3. Thank you so much for watching to the end. Make sure to check out this video for more video tutorials.